Welcome to Math 31, Lesson 2, Differential Equations. So what we're dealing with here is an extension of the lesson yesterday where we were discussing the C value for constants and how we are unable to uniquely define an antiderivative unless we're given more information. So this is where this is going. Now, in general, an equation that requires you to get an antiderivative is a differential equation. So typically you'll be given a function and you will need to differentiate it in order to get whatever information you want. And a typical question, at least that's not attached to any application, would be this. Solve this differential equation. So there's the derivative, 6x squared plus x minus 5, with the boundary value f at 0 is equal to 2. And the boundary value f at 0 is equal to 2, also referred to as, in fact more commonly referred to as initial conditions. And what these initial conditions are, one way of looking at it, is that they represent a point on y equal f at x. And that's what you need. In order to get the equation for f at x precisely, we need to have a c value, or we need to have one point on the curve that we can substitute in to solve for c. And for the next week or so, that's going to be a big challenge in applications or whatever sort of algebraic context, is to find those initial conditions. Not always stated clearly, like in this case. But for us, to finish this one off, we now get the antiderivative. So f at x is equal to exponent first, x to the 3, and then 6 over 3, and then plus x to the 2, and then 1 over 2, and then minus 5x plus c. Now simplifying it, we get f at x is equal to 2 x to the 3 plus 1/2 x squared minus 5x plus c. Make sure that's a c, not a 6. Then we do know that f at 0 is equal to 2. So now it's just a matter of making the replacement in. So 2 is equal to 2 times 0 cubed plus 1/2 times 0 squared minus 5 times 0 plus c. Do the math on this one and you will get c is equal to 2. And this tells us then that the function f at x is equal to 2x cubed plus 1/2 x squared minus 5x plus 2. So that's the question. That's how these things go. Now, usually it's not stated so clearly what the initial conditions or the boundary value is or are, so you have to do a bit of work on it. So this is an example, a pretty good question. Mathematically very easy, but making sense of it is the challenge. We're told that this line, y equal 2x, is tangent to the graph of this unknown function, f at x. It's unknown because we do have the derivative, f prime at x. Now, we can do this one in a few different orders. Some of you will think right away, well, I need to get the antiderivative of this function. And, of course, what you get is f at x is equal to x to the 3, and then 2 over 3 x to the 3, and then plus c. But we do need to find out what the c value is. So we need to find c. Now there is information here. We're told that y equal 2x is tangent to the graph. Now it's important to remember that if y is equal to 2x, this m, the slope, is equal to 2. And that's significant because the slope of the tangent line is the derivative. So it means f prime at x is equal to 2. And we want to find the x value where the derivative f prime at x is equal to 2. Also should say with this question, I left it out of the original, but it's supposed to be there. This is in the domain 0 to positive pi. So I'm just taking the positive value. It's not a big deal. It just means that if we're going to, you'll see soon that we'll get two answers otherwise, and the point is adequately made with just the one. So I'm going to put that domain in there. It should have been in there. So now all we got to do is set the derivative to 2 and solve for x. So x squared is equal to 1. Then I'll take this up and over. X is equal to plus or minus 1. But of course we just want x equal positive 1 in the domain. Now we have the x coordinate for these initial conditions. But if we want to find the y coordinate, we've got to think a little bit. It's not stated clearly. However, this line y equal 2x is tangent to the graph and is actually touching the curve at x equal 1. So therefore, at that point, they're coincident, and meaning that the y coordinates will be the same. So all we got to do is substitute into y is equal to 2x. So y is equal to 2 times 1, or 2 times 1. So y is equal to 2. So our initial conditions are x is 1 and y is 2. And now we are in business. I'll just bring up a new screen in a second or two. But we've got everything we need. We've got our antiderivative plus c, and we just plug in our numbers. So x is 1, 2. The function f at x is equal to 2/3 x to the 3 plus c. So the 2 goes in for the y, 1 goes in for the x. So 2 is equal to 2/3 plus c. So when you subtract 2/3 from 2, you get 4/3. 6/3 minus 2/3. So therefore, the function f at x is equal to 2/3 x to the 3 plus 4/3. Type of thing you can do. So a good question. Now the next one I'm going to look at is an application. And although it's not going to be a real killer application, it does give you an idea of how these things work. And what you're going to be noticing, if you haven't already, is that we're doing the exact opposite to what we were doing before. And it's more pronounced on these applications. Because in this case, the population is of this town or city in Minnesota is growing at a specific rate, where t is the time in years since 1970, and the rate r is measured in people per year. And eventually we want to find the population in 2006. And you're probably thinking, as am I, that the formula that you were given does not give you the population. It gives you the rate that the population is changing. So we need to get this. And p at t, let's say, use any variable you want, is population. And this makes sense to introduce an equation we can work with. So I'm just going to call this a population at time t. Now time t is years since 1970. Also, this should make sense. P prime at t, the derivative of the population function, is equal to the rate of growth function, r at t. So it means we need to find the antiderivative of the function. So P at t would be the antiderivative of RT. So we take that equation and get 2t. So we add, remember this is like t to the 0 if you thought of it in those terms. And then the next one would be plus, do the exponent first, t to the 5 over 2, so add on 2 over 2. And then this becomes 10 divided by 5 over 2. Now, I don't know why I didn't do that in one step, but I guess I didn't. Take it now. So 2t, this is 10 over 1 times 2 over 5. So it should be plus 4 t to the 5 over 2 plus c. And we're looking for initial conditions. And this is given to us because it tells us that the population in 1979 is 2010. So that's 9 years after 1970. So it tells us that the population after 9 years is equal to 2010. And now we're good to go. I'm going to bring up a screen to get some space to work. But we now write this as 2010 is equal to 2 times 9 plus 4 times 9 to the 5 halves plus c. So you can do this a number of ways. I'm going to do this one almost too slowly. This is 18 plus, you work out this term, and you could have just gone straight through this one. It's going to work out cleanly because 9 to the 5 halves is a whole number. So 4 times 9 to the exponent of 2.5, which is what that's equal to, is going to be plus 972 plus c. So now we just clean this whole thing up. 2010 minus 18 minus 972 is 1020. So 1020 is equal to c. So therefore the population function, p as a function of t, is equal to 2t plus 4t to the 5 halves plus 1020. And we want the population in 2006. So remember again, we're taking it from the year starting at 1970. So therefore that means P at 36 years after 1970 is equal to 2 times 36 plus 4 times 36 to the 5 over 2 plus 1020. So drive that straight through. 2 times 36, 72, plus 4 times 36 to the exponent of 2.5 plus 1020, and we're going to get 32196. So P at 36 is equal to 32196. So Starbucks population in 2006 is or was 32,196. Those of you who've been to Starbucks recently will know that that seems to be an exaggeration by quite a bit, but mathematically it is correct. So I'm going to stop right there, and then the other questions that I'll do later are going to be motion problems involving antiderivatives and differential equations. So thank you for your time.